So heuristic algorithm is a method and strategy seeking to solve problems, which is based on experience and judgment. It reflects the subjective initiative and creativity of the algorithm designer. Common heuristic algorithms for facility locations include genetic algorithm, simulated annealing algorithm, particle swarm algorithm, artificial neural network, and many others. Generally, these algorithms follow a similar process. So we take genetic algorithm as example here. You may watch this video to get an overall understanding of genetic algorithm.
Genetic algorithms are an optimization technique used to solve nonlinear or non-differentiable optimization problems. They use concepts from evolutionary biology to search for a global minimum to an optimization problem. The name genetic algorithm comes from the fact that they're mimicking evolutionary biology techniques. Genetic algorithms work by starting with an initial generation of candidate solutions that are tested against the objective function. We then generate subsequent generations of points from the first generation through things such as selection, crossover, and mutation. Let's take a look at these different techniques, selection, crossover, and mutation, on an example of a binary problem where the variables in the optimization problem can either take on a value of 0 or 1. Selection means to retain the best performing parents from one generation to the next. So in other words, if we have parent 1 from the previous generation and parent 2 from the previous generation, and these are the values of the variables in the optimization problem, through selection, those make it through to the next generation just because they performed well in the previous generation. Now, because they performed well, they might also be used for crossover. And in crossover, what we do is we select common similarities between the different parent variables and keep those the same to create children variables that will be in the next generation. The last thing that happens is what's known as mutation, where we take a parent and mutate certain variables to take on random values, and we create a child based off of the mutation. Mutation allows genetic algorithms to kind of avoid falling into local minima, and it really helps them explore the solution space well. So let's see an example of how this might work on an optimization problem of two variables, x and y, and the three sets of contours that we have here are each different minima to the optimization problem. Now the green minima and the red minima are local minima, while the blue one actually happens to be a global minimum. The yellow dots on here are the initial points, or the first generation for my genetic algorithm. So the first step that the genetic algorithm does is it evaluates all these points and it determines the fitness function value for each one of them. The next thing that it'll do is it'll select a few good solutions as the parents to continue on to the next generation. So these green points here did well, we'll keep those for the next generation, and we'll also use them to create the subsequent generation. So for iteration 2, we generate those new points through selection, crossover, and mutation, and then we evaluate the new population. We then repeat this process of generating new generations until the algorithm converges. Genetic algorithms can converge through a variety of convergence criteria. A couple popular ones are a fixed number of generations, so the genetic algorithm will just run until it's hit a certain number of generations. Another one is it will converge when the best objective function or best fitness function value is no longer changing, or it's changing by a really small amount. And take a look at an example of a genetic algorithm on our peaks problem. So the peaks problem is a problem that has a couple different local minima. It's actually the same function that we were looking at in the slides. And it has a global minima down here. So again, two local minima and one global minimum over here. So I'm going to set up an optimization problem for the genetic algorithm. I'll give bounds of -3 on both of the decision variables and an upper bounds of +3 on both the variables. And we'll tell the genetic algorithm to solve our problem. So you can see here on the plot the different points being evaluated by the genetic algorithm as it progresses. Now, the dots down here at the bottom are kind of all the historical points that were evaluated, and we can see that the genetic algorithm pretty quickly got into the best minimum over here and converged down to the global minimum of this problem. So while it did explore spots over in the local minimum, it was able to avoid getting trapped in one of those local minima, though, and it ended up finding the global minimum.
For a particular problem, chromosome coding of genetic algorithm is the basic but very important step. For the facility location problem we formulated in last course, you can use gem blocks like this. The number of rows corresponds to the number of candidate facilities, and the number of columns equals to the number of customers plus 1. So the first column represents whether selected the facility or not. Each of the rest column represents whether the customer is arranged to that corresponding facility or not. So based on the coding, you can carry on the genetic operations. The fitness function is used to estimate the performance of the solutions. So it's always correlated to the objective function. Here we can take the reciprocal value of the objective function. Okay, that's everything for genetic algorithm. We introduced several methods for location problem in this course. It may be difficult for you to grasp all the algorithms, but no problem, just to focus on the specific ones that you are interested in, okay? So next time, we are going to understand algorithms for distribution optimization. Okay, thank you and see you.